Hey everyone, my name is Lily, and thank you so much for tuning into this talk. I'm a rising senior at UC Berkeley, and today I want to share with you a recent project that I did over the summer. Most of the math is done with my group member, Caleb Partin, and under the mentorship of Professor Dan Margalit at Georgia Tech. So we'll start with the basic question. In this talk, we're interested in polynomials. In particular, we care about polynomials acting on the complex plane, or the Riemann sphere. So now you could see polynomials as merely a function from C to C that acts like a black box. You put in some numbers as inputs and it gives you some outputs. But more relevantly for this talk, we care about polynomials as it transforms the complex plane, and this is the viewpoint that we have to adopt. So here's the question. Let's get a picture on here. Ooh. There we go. So every polynomial is a transformation from the complex plane to itself. But how do we reconcile the reverse problem? How do we recognize polynomial transformations out of the vast selection of different transformations? In other words, if someone hands you a map of the complex plane to itself, then how do we know if it's a polynomial? And if it is a polynomial, which one is it? Now, how does one specify a map in the first place on the complex plane? We can look at the picture on this slide. In this graphic, we first color all the complex numbers as on the left picture, with colors, and then draw in the unit circle in gray. So essentially, we've assigned a color to every number, and it shows the unit circle. Now, then to specify a polynomial, we take the pre-image of the left under the polynomial to get a picture on the right. So looking from right to left, we're looking at a correspondence that if a point is red on the right side picture, then it'll map to the red value on the left under the polynomial. So in some sense, this picture captures all the information stored in a polynomial. The particular picture on the right is sort of randomly chosen. I just picked z squared plus 1. And we can see that since it's a quadratic, there's a 2-to-1 correspondence, that there are 2 copies of almost color region. This is just because there are 2 pre-images for most of the points in their neighborhoods. For example, if we look at this on the left, this region next to the origin, in black and white, then we can see 2 corresponding to it, here and then here. You can do the same with this red and black little wheel. There's 2 copies here and here. And this happens for most of the points, except for this point right here. So right here, we see that this green wheel from the left only appears once on the right side, even though we somehow expect it to appear twice. And this is just because it's a critical point. So all it says is that if you take the derivative set equal to 0, this is the point you're going to get. So there's only 1 copy of this point. Okay, so for the most part, there's a 2-to-1 correspondence. And if it makes any sense, it's a branch double cover over that point. And we can say that we can say this about any polynomial transformation, that roughly it looks like n copies of the plane sewn together at these critical points, or that it's always a branched cover. At the end of the day, anyone could hand you something like this, just a picture of just a coloring like this, and ask, is it a polynomial, and what kind of polynomial is it? So since these maps are the object of study, let's see a few examples of them, or a few more examples. Before we can answer the question of like which polynomial is something, maybe that's a harder question, we can ask ourselves, are certain polynomials the same one? So here are 3 pictures of some polynomials I graphed. And on the left side, we see something that is very similar to the previous picture. You see 2 copies of almost everything. In particular, you see 2 copies of this origin neighborhood, 2 copies of the red and black wheel that we're looking at. And then in the middle, there's some critical point thing happening. And for the most part, this is as we expect. So in some sense, we're fairly sure that this is a quadratic of some kind. In the middle, though, we see that there's a tripling action going on, in a situation where we see 3 streaks of every color, 3 streaks of yellow and red and so on and so forth. And we see 3 copies of the unit circle meeting at some critical point. So we're probably thinking that this is like a cubic, so not quite a quadratic as we've been seeing. And we should immediately notice that if 2 polynomials are of different degree, then they're definitely not the same polynomial. But then if we look at the second picture and the third picture and compare them, we see that they're kind of different, but in some sense they're both cubics, right, on the right side, you still see this tripling action that you see 3 copies of this origin thing, and then 3 copies of the red and black circle that we've been looking at. The only difference is there's some weird thing about perhaps having more critical points or something. So in this sense, just comparing the degree is not quite enough to tell which polynomial something is. So we'll have to look at more information. There's more to the recognition problem. So the next thing we might want to look at is portraits. So what's a portrait? Here's a description. So in addition to looking at the degree, we kind of care about critical points. So we take all of the critical points that we've gathered by doing the derivative trick, just setting equal to 0 and finding the roots. Now we can take the critical points and plug it back into the polynomial to get these forward images of the critical points. So for example, if on the picture my red point z0 is a critical point, then I could substitute it into the polynomial to get p of z0, in which I get z1, plug it back into p, we get z2, so on and so forth. So the sequence of points from z1 onwards, not including z0, are the forward images, and we call them post-critical points. For the most part in this discussion, we care about post-critically finite polynomials, which just means that we want there to only be a finite set of these z's. All right, so let's look at a couple of examples. One of our favorites is z cubed, just z to some power. We see that the critical point happens at 0, and 0, if plugged into the map, 0 goes to 0. So 0 is not only a critical point, but also a post-critical point. And it turns out to be the only post-critical point in the post-critical set. Okay, so what about z squared minus 1? So in this case, 0 is again the critical point, and we plug it back in to get -1, and -1 goes back to 0. So this again loops back. It is a post-critically finite polynomial, and -1 and 0 are both post-critical points, just because they're at the end of the arrow. So in both of these examples, we see a cyclic action going on. So the portrait is cyclic. And so you might be asking, what if I add more points into my post-critical set? And what if, say, I want to know what the polynomial with a post-critical set of a cyclic portrait of 3 post-critical points might look like? Well, you're in luck, because this is one of our favorite polynomials to study in this subject, which is the rabbit polynomial. So the rabbit polynomial also has a portrait that just looks like the picture on the left, where we have the critical point mapping to some other point, and then back to that point. That doesn't make any sense, but it's a cyclic portrait of length 3. Okay, so the reason it's called the rabbit polynomial is because if you graph the Julia set of this polynomial, it kind of looks like the middle picture where you have these little ears sticking out, and mathematicians called it the rabbit polynomial. So if just going back to the pictures that we've been seeing, the rabbit polynomial looks like this picture that we've been discussing. So as we expected, it's a quadratic, and it has this 1 critical point in the middle. Okay. All right. So maybe your question is now, given a particular portrait, is it true that there's only one polynomial associated to it? So for example, I sort of lied in saying, here's a portrait, this is the rabbit polynomial corresponds to it. What if there are other polynomials that correspond to it? And you would be correct, because in this particular case, there are 2 other quadratics that have the exact same portrait as the rabbit polynomial. And these are called the airplane and the co-rabbit polynomials. On the left side is the co-rabbit. So it looks like the rabbit, but sort of just put on its side. And again, you see the 2 ears coming out. And on the right side, we have the airplane polynomial, where you see this Julia set that looks kind of like an airplane. Okay, so now this is kind of disappointing, right? Even though we have all these really pretty pictures, the portrait, so the critical points and their images don't actually tell us exactly which polynomial it is. So the question comes, well, what is the minimum amount of information you need to specify a polynomial up to some kind of equivalence, right? So we look at trees. And again, the question we're answering is, how much information do we need to determine the polynomial uniquely up to some sense of equivalence? So the Alexander method tells us that, in fact, there's not too much information involved. A topological polynomial is completely determined by its actions on a single tree. So what does that really mean? So loosely, we can look at the picture and see what's going on here. So on the bottom left corner, and we see this little tripod, and this is the tree associated to the rabbit polynomial. So there are different trees associated to different polynomials, and this one in particular is associated to the rabbit polynomial. And so we want to take its pre-image under the polynomial, and taking the pre-image, we see a doubling action right here, and we get this double tripod situation. So just this tree on the bottom and its pre-image will determine for us completely which polynomial it is, up to equivalence. So this is the rabbit polynomial. So what is this equivalence, you might be asking? This equivalence just means that if you sort of perturb the plane by a little bit, it's still the same polynomial, just drawn in a different way. So the picture on the right, we see that all you do is swing this arc a little bit and maybe have a little curvy action going on here. They're still essentially doing the same thing. These two polynomials described on the left and on the right, in some sense, work the same way on the important sets of information. So we say that they're a Thurston equivalent. They're, in some sense, the same polynomial. Okay. So all this while, we've been starting with the polynomial. Remember, at the beginning of the talk, we were saying, if you're just given some random transformation, how do you tell it's a polynomial? But then following that, we have been just saying, given a polynomial in the first place, how do we tell? How do we sort of extract information? So now, if I take the rabbit polynomial and I modify it in some way, I could use that to answer the. I could answer the question. Is it still a polynomial? If I have a modified version of the rabbit, is it still a polynomial? And which one is it? So we're going to do exactly that. So how do we modify the rabbit polynomial? Well, we can compose it with something else. So we do the rabbit polynomial. We compose it with another map from C to C, so that the composition is still a transformations complex plane. And the things that we want to compose by are homeomorphisms of the plane that fixes the post-critical set. Because in some sense, we want to keep the post-critical set intact. So the some examples of the homeomorphisms we can compose with is Dane twists. So what is a Dane twist? We can take a curve C on the complex plane that misses the post-critical points, and then we take this curve and take this little annulus neighborhood just around it, like the picture here, and then we cut it open. We cut along C into two, so that we break the annulus into two, and then we take one of the copies and start dragging the boundary by turning it around until we get a full turn, get a full rotation, and then gluing it back on. So in some sense, apart from the neighborhood of C, nothing has really happened, except around C, we've added a full turn in the surface. So seeing what it does on this curve, so this little green segment here that crosses C directly, after the transformation, will have to go around C and then back in, illustrating this full turn. So the question becomes, well, say this is the polynomial, this is the rabbit polynomial, and the tree associated to it in the complex plane. If we compose the rabbit polynomial with this Dane twist that happens, around its two ears, then we can make some observations about the resulting map. So first of all, the degree is preserved, because if you had a doubling action in the previous case, this turning doesn't actually destroy your doubling. And then the post-critical set is preserved because, as we said, the Dane twist doesn't actually touch anything other than the immediate neighborhood of the curve that you're twisting on. So the post-critical set is still those 3 points. And then the portrait is preserved in some sense, right? Because the Dane twist doesn't touch the post-critical set. So now the question comes, well, all these things are preserved, but is it still the rabbit polynomial? If not, what is it? Is it still a polynomial? It turns out that that mathematicians have already answered this problem. So in 2005, Bartoli and Nekrashevich answered the problem for the rabbit polynomial by classifying what each Dane twist and their powers could do to modify the rabbit polynomial. So they prove that if you take any twist, you'll end up getting one of the three polynomials that we've been discussing that has a cyclic portrait and it's a quadratic. So again, it's because the degree is preserved, post-critical set is preserved, and the portrait is preserved, that we're limited to only three possibilities: the rabbit, the co-rabbit, and the airplane. So Bartoli and Nekrashevich give a full classification of, given some set of twists, what kind of polynomial you get in the output. So what did we do this summer? Not only do we want to sort of look at the rabbit polynomial, we want to look at a larger class of polynomials. So for example, what if we modify the portrait so that it's still cyclic but of length 4? In that case, we get some polynomials, including the 3-eared rabbit polynomial. So this is kind of still the rabbit, except you get a 1 extra ear on its head. And the Julia set looks something like this. And now, given this rabbit, you can imagine that there are more twists and more modifications you can do. And we want to classify, what are all the homeomorphisms that you can compose with? And it turns out that all the homeomorphisms of the complex plane fixing the post-critical set is generated by just compositions of these twists around these ears. Now, so we try to answer this question of, given some set of, given any homeomorphism, how do we write it as, how do we understand it as, one of the other polynomials that are candidates for what can we twist to? So polynomials with the post-critical set, with a portrait that's cyclic of length 4. So in that sense, not only do we want to consider, one twist or powers of the same twist, but we want to consider compositions of twists around different ears. So for example, what if I want to twist around this red curve a couple of times, and then compose that with the twist around these other 2 ears? So what is that going to give us? So that's the question we've been trying to answer this summer. And in a short summary, that this is what we did. So there's a subgroup of all the twists called L mod. These are the liftable mapping class groups. What do we mean by liftable? Liftable just means, well, we care about lifting because it turns out that there's an operation called lifting that preserves the equivalence class of the polynomial. So maybe I have some set of twists that I'm composing with a rabbit polynomial, and then by lifting them, I get another set of twists that give you the exact same polynomial. So the hope is that by lifting a bunch of times, we'll get something that's really simple. That's really simple, and that we can say, okay, this is the rabbit polynomial, or this is the co-rabbit polynomial. So in our research this summer, we fully described the virtual endomorphism form from the liftable mapping class group to all the twists for the n-eared rabbit polynomial. And this gives us a way to solve the 3-ear rabbit polynomial recognition problem, the one that we've been discussing, where the rabbit has 1 extra ear. And then in the end, we give some algebraic structure on the subgroup of all the homeomorphisms that we care about with respect to a sequence of n-eared rabbit polynomials. So if I have 3 ears, 4 ears, 5 ears, 6 ears going up, then what can we say about how the different L mods behave with respect to the sequence of polynomials? Okay, so this is the end of my talk. Thank you so much for coming. I hope you enjoyed it, and bye.